Uh, Hello friends, welcome back to my YouTube channel. Welcome to my discussion on tall columns. This is part 3 of that discussion, and in this I'm going to talk about analysis of stresses that are induced in the wall of a typical tall column. And today I'm going to talk about stresses that are induced due to dead loads. In my earlier discussions on tall columns, in part 1 I have introduced tall columns to you, and I have given a brief introduction to stresses that have to be considered while designing tall columns. Then in part 2 I talked about stresses that are induced due to internal pressure, external pressure or vacuum in the wall of the tall column. So those of you who have not yet seen my those videos, you please go and watch those videos. I'm giving link to those videos in the description section. For now, let us talk about stresses that get induced in the wall of the tall column due to uh, various dead loads. To begin with, let us understand what are the loads that will induce stresses into the wall of the column. So internal pressure, external pressure or vacuum, and these are going to induce longitudinal and circumferential stresses. I have already discussed this in part 2. The nature of these stresses will be they will be tensile and they will be compressive. Then dead loads, they are going to induce longitudinal or axial stresses in the wall, and nature of these stresses is compressive. Wind loads, they are going to induce longitudinal stresses again, and nature of the stresses will be tensile and compressive. Then eccentric loads, they are going to induce longitudinal or axial stresses, and nature will be bending. This will be bending stresses. Then seismic loads, again they are going to induce longitudinal, that is axial stresses in the wall, and nature of the stresses will be tensile and compressive. For today, I'm going to talk about stresses that are induced due to dead loads. These stresses will be acting in axial direction. That's why we are calling them as longitudinal or axial stresses, and the nature of the stresses will be compressive. ठीक है. What dead loads are considered for calculating stresses? Let me tell you first. So we are going to consider weight of the shell itself. Then I'll be considering weight of the insulation, weight of the liquid on the trace. As I said earlier, in the beginning of my discussion on tall columns, I had said that I'll be talking about tray columns. So weight of the liquid on those trays, that also have to be considered. And then uh, uh, liquid on trays is nothing but liquid holdups on those trays. Then weight of attachments, various attachments like trays, downcomers, weirs, overhead condenser, top head, platforms, ladder. ठीक है, so let us start with analyzing the stress that will be induced due to the weight of the shell. So for that, we will consider consider the column, and now you can see you have the column, and the column will be having shell and then the heads, top head and head at the bottom. Let DO represent the outer diameter of the shell, and DI represent the inner diameter of the shell. And then we are going to consider a plane at a distance of x from the top of the column, from the top of the shell. So we are not considering head in our discussion. We are considering from the top of the shell. So we are considering a plane at a distance of x. We have selected this section in such a way that thickness of the column within this section is uniform. Height of X is selected in such a way that the thickness of the shell is uniform throughout this height. Then let Ts represent the thickness of the shell. Now weight of the shell for the selected distance. So we want to know what is the weight of the shell for this much portion. Okay, so let us denote it as Ws. So Ws will be pi by 4 into dO square minus di square. So dO pi by 4 dO square minus di square will give us this area. So we are considering cross-sectional area based on the outer diameter and then deducting cross-sectional area based on inner diameter from it. So you get area of this portion. Okay, so that area will be coming into picture while calculating weight of the shell in that portion. So pi by 4 into dO square minus di square into x. So area into height will give you volume of that section, and then when you multiply this with the density rho s, you get the weight, and when that is mass in kg for example, and when you multiply this with acceleration due to gravity, you'll be getting weight in Newton. So that means this formula is going to give us weight of the shell in Newton. dO is outer diameter, di is inner diameter of the shell, Ts is thickness of the shell, the notations that are there in this equation, and rho s is density of the shell material, and g is of course the acceleration due to gravity. Okay, so let us continue further. Now the weight that we got on previously, this weight will be acting on the area that is given by A is equal to pi by 4 into dO square minus di square. That means this area will be taking that weight, or in other words I am saying that area on which Ws acts is A is equal to pi by 4 into dO square minus di square. Then the compressive stress that will come into picture due to Ws acting on A will be given as FCS, compressive stress due to shell weight, is equal to Ws upon A. Ws we got it previously, pi by 4 into dO square minus di square into x into rho s into g. So if you put that expression in this, you get FCS is equal to pi by 4 dO square minus di square into x into rho s into g divided by pi by 4 dO square minus di square. So pi by 4 into dO square minus di square gets cancelled, and you are left with FCS is equal to x into rho s into g. So this expression gives us the compressive stress that will be induced in the shell wall up to a distance of x from the top of the shell. Then let us talk about the stress that is induced due to the weight of the insulation. So again I am showing you the column with outer diameter dO, inner diameter di, thickness Ts, and now we are considering the insulation. With insulation, the insulation diameter, let us denote it as din. Again we are going to consider a plane at a distance of x from the top. The thickness is uniform. The plane is selected in such a way that thickness above that plane is uniform. So we are considering a section from the top at a distance of x, and then tin, let us denote thickness of the insulation as tin. Now weight of the insulation we need to calculate, and then this weight will be taken into consideration for calculating stress due to its weight. So the weight of the insulation, let us denote it as Win. So Win will be equal to pi by 4 into din square minus dO square. So we are taking this area into consideration. So area based on din, this area minus area based on outer diameter do. So that will give us area of the insulation, area occupied by the insulating material. So Win is equal to pi by 4 into din square minus do square into x, because we are considering it up to distance x into rho in into g. So again, this weight is going to have an unit of Newton. So you can check with this. So Win, we get it as pi by 4 into din square minus do square into x into rho in into g. So din is insulation diameter. I'll tell you how to get that. Do is outer diameter of the shell. Rho in is insulating material density. G is acceleration due to gravity. And how is din obtained? Din is given by this formula. Din will be outer diameter plus 2 times the thickness of insulation. So if you need to calculate, din, and you can calculate it by using this formula. So din will be equal to d0 plus 2 into din. Okay. Now let us continue. Now area on which the weight of insulation acts, area on which Win acts, is again this area. A is equal to pi into di plus ts into ts. So this will be the area on which weight will be acting. Weight of the insulation will be acting. Here in this case, di plus ts is nothing but the mean diameter, which is mean of outer and inner diameter. You can check that. So if you simplify this, you do some analysis with this, you'll get this equation. So di plus ts is nothing but the mean diameter. Therefore, uh, the weight of the insulation is going to act on this area. Okay. Now the compressive stress due to Win, weight of insulation acting on E. So let us denote it as FCIN. So FCIN will be equal to Win by E. Win, we already got it on previous slide, pi by 4 into din square minus do square minus x, sorry, into x into rho in into g. So if you put those values, we'll get FCIN is equal to pi by 4 into din square minus do square into x into rho in into g divided by pi into di plus ts into ts. And after simplification, you'll be getting this. FCIN is equal to din square minus do square into x into rho in into g divided by 4 into di plus ts into ts. So over here pi is getting cancelled and we are simplifying the equation in this way. So this gives us the stress, the compressive stress that is induced in the wall of the shell up to due to insulation up to a distance of x from the top of the shell. Okay. Now let us talk about stress that is induced due to weight of the liquid. So again I am considering the column. Now where is the liquid coming from? You have liquid hold up on each tray. And on each tray, in order to have that liquid hold up, liquid height is maintained by the outlet weir. So I'll show you this. I will show you that in this diagram. First, you just understand. You have liquid hold up on each tray. The height of the liquid on each tray is maintained by outlet weir, and above the topmost tray in the column there is a disengaging space. A disengaging space above the topmost tray. So I'm showing you the topmost tray. You have the outlet weir for this tray and then the downcomer. Then on this tray there will be liquid hold up, and height of that liquid will be maintained by this outlet weir. Then I was talking about the disengaging space. What is this space? It is the distance from the topmost tray to the top of the shell. So within this space, vapor and the liquid, these two phases will be getting separated. They will be getting separated, or the vapor that is rising out of this tray, it will be getting separated, from the liquid in this space. Okay, so let us say that the length of this disengaging space is LD and height of the weir is HW. Okay, so height of the outlet weir is HW, height of the disengaging space is LD. Due to HW, we are going to have a liquid hold up on the tray up to a height of HW. Uh, so the disengaging space, it will not contain any liquid in it. As far as liquid on the tray is concerned, the liquid hold up on the tray, on the topmost tray, that is this liquid. Uh, when I say the disengaging phase will not contain any liquid in it, then you must be getting confused. How is this possible when you have this liquid on the tray? This liquid is considered in a different way. We are going to consider that separately. So that will be considered when you talk about the topmost tray. For now, you should understand that in the disengaging space within this height of LD, there will be no any liquid in it. The weight of the liquid in the column will be sum of weights of liquid on each tray. So for you need to consider all the trays. If you have to talk about weight of liquid in the entire column, you need to count all the trays, and for each tray there will be a liquid holdup, and you need to calculate weight of that liquid holdup for each tray, and the sum of weight of liquids on all the trays will they'll give you total liquid holdup in the column. Okay, so let us continue. Now again we have this diagram. Now as usual, I'm going to consider a plane at a distance of x from the top. How is this considered? This is considered so that you have uniform thickness in that section. That means from the top to this point, distance is x and thickness for the shell is uniform within this section. Okay, then you have outer diameter, inner diameter, diameter of the insulation, then thickness of the shell as usual, then thickness of the insulation TIN. Okay, now weight of the liquid in the selected section. Now task is to get weight of the liquid in the selected section, that is this distance. So for that we need to know number of trays in this section, weight on each tray. Weight on each tray into number of trays in this section will give you weight of liquid in this section. Okay, so weight of liquid in the selected section is sum of weights of liquid on each tray in the selected section. This is clearly understood. Now in the selected section, trays will be equally spaced within a height of x minus LD. Now tray has to be spaced. Now if you talk about this distance, out of this distance, LD will not have any distance, the LD height will not have any tray in it. So all the trays that are present in this section will be lying within this distance. And what is this distance? X minus LD. So that's why I'm saying in the selected section, trays will be equally spaced within a height of x minus LD. Tray spacing, what is tray spacing? You know, this is distance between two consecutive trays. So tray number 1, tray number 2, distance between these two tray will be the tray spacing, and it will be similar for any two consecutive trays. Let us denote tray spacing by yes. I'm going to denote tray spacing by yes. Okay. So with this understanding, let us know number of trays in the selected section. So number of trays within a height of x minus LD with a tray spacing of s. So why x minus LD I have already discussed, and you have tray spacing of x. So within this distance with tray spacing of x, you will have number of trays as x minus LD upon s, that is the total distance divided by tray spacing, number of trays, plus 1. There will be one more tray. I'm going to explain that. Okay, so for time being, you understand that number of trays within this height with tray spacing of s is given as n is equal to x minus LD upon s plus 1. To understand this, what we will do, we will consider a height of 5 meter. Now number of trays with a tray spacing of 1 meter. Let us try to find out what is the number of tray with a tray spacing of 1 meter. So I am showing you the height. So let us start with, we have to start at the top. So this is tray number 1. Next tray will be placed at a distance of 1 meter since tray spacing is 1 meter. Next tray after a tray spacing of 1 meter. Similarly with tray spacing of 1 meter, you'll be having number of trays that covers the entire distance. Now you have 1 meter plus 1 meter plus 1 meter plus 1 meter plus 1 meter. This entire height now comes out to be 5 meter. We have used a tray spacing of 1 meter. Now let us count the number of trays that will be involved in this. So this is tray number 1, tray number 2, tray number 3, tray number 4, tray number 5, and tray number 6. That means within a height of 5 meter with tray spacing of 1 meter, we can accommodate 6 trays. That is, one additional tray is accommodated. So based on the height and tray spacing, you can calculate whatever you get, whatever number of trays you get, you have to add 1 to that. So according to this particular discussion, you have this equation. So whatever tray you accommodate within the height of x minus LD, you have to add 1 to that. That's why number of trays within a height of x minus LD with the tray spacing of s is n is equal to x minus LD upon s plus 1. Okay, I hope this is clear to you. If you have any doubt, again you please let me know. Now weight of the liquid on n trays. If you denote it as WL, it will be n into weight of liquid on each tray. N we already have got an equation for that, x minus LD upon s plus 1. Now let us get W, weight of liquid on each tray. So this will be given as volume of liquid on that tray into density of the liquid. You please read it as density of the liquid. Let us denote it as rho L. Now for that, first let us obtain the volume of the liquid on a tray. How it is obtained? For that, you just look at this tray. The tray space occupied by the tray is this one. This space is not occupied. This space is open. The space is open, so the space is occupied by the downcomer. So liquid will be flowing down to the next tray through this downcomer. Now let the length of the downcomer, length occupied by downcomer, let us denote it as HD. Okay, so liquid on the tray will be lying on the tray in this region. That means it will be covering a distance of internal diameter minus this space. This we need to know this distance. So this distance will be the diameter, internal diameter minus this distance. That's why volume will be pi by 4. And now you have to update the diameter by deducting the space occupied by the downcomer. So it will be di minus hd square into height of the liquid on that tray. So VL will be pi by 4 into di minus hd square into hw. So W is obtained in this way. Pi by 4. Now you can directly go with this formula. You have got VL, that is volume. So W will be pi by 4 into di minus hd square into hw into rho L. So this is weight of liquid on one tray. So once you have got weight of liquid on one tray, it is easy to get weight of liquid on n trays. So WL will be n into weight of liquid on each tray. You have equation for n, x minus LD upon s plus 1. Equation for W, pi by 4 into di minus hd square into hw into rho L. So you just have to put the equations, corresponding equations, and you get this equation for WL. So weight of liquid on n trace within the section of height x will be x minus LD upon S minus 1 into pi by 4 into di minus HD square into SW into rho L. Now you have to talk about the stress. You got equation for WL, and now it is acting on this area. Which is this area? It is A is equal to pi into di plus ts into ts. Di plus ts is nothing but mean diameter. I have already talked about it. Now the stress due to WL acting on A will be FCL. Let us denote the stress as FCL, compressive stress. FCL is equal to WL upon A. WL, we have got the equation for it, x minus LD upon S minus 1 into pi by 4 into di minus HD square plus HW, into HW into rho L. And if you put A, you already have equation for A. So if you put the values, if you put the corresponding equations, you will get equation for FCL. So FCL will be x minus LD upon S minus 1 into pi by 4 into di minus HD square into SW into rho L divided by pi into di plus TS into TS. So that gives us compressive stress that will be induced in the wall of the column due to the weight of the liquid in the column. Okay, now let us understand the stress that will be induced due to weight of attachments. So due to the weight of the attachments, you have different attachments. So you have manhole, railing, then ladder, platform, trays, downcomers. So what are the attachments? Trays, downcomers, weirs, overhead condenser, top head, platforms, ladders. So we need to consider all these attachments for calculating the stress. Now let us denote, let us consider all the attachments and let us denote the weight by WA. So let WA represent weight of all the attachments for the selected section, and this weight of all the attachments will be acting on area, that is again pi into di plus ts into ts. So therefore the stress that will be induced due to weight of attachments that will be acting on A, and this will be compressive stress. So it will be up C AT is equal to W upon WA upon A. WA is you have the weight, and now area is 5 into di plus ts into ts. Okay, now let us know weight of various attachments as it is given in few literature. So as available in the literature, you have weights given to various attachments. So for example, for steel platform, it is said that the weight is 1.67 kilonewton per meter square of the area. So per meter square area of the column, cross-sectional area of the column, weight for steel platform can be taken as 1.67 kilonewton per meter square. For steel ladder, which is caged, that means a ladder that will be covered with a kind of cage. So for such ladder, the weight that you can consider is 365 Newton per meter. 365 Newton per meter length of the ladder. Then if you talk about simple or plain ladder without any cage, then for plain steel ladder, you can take the weight, its weight as 146 Newton per meter ladder length. Then trays with liquid holdups, you can take the weight of those trays as 1.2 kilonewton per meter square tray area. So these values are available in literature, so you can use them in absence of any relevant data. Now if the column does not contain trays, if the column is not containing any trays, then you can consider the weight of attachment to be 18% of the shell weight. So if you know the shell weight, and if the shell is not containing any trace in it, then weight of all the attachments, it can be taken as 18% of the shell weight. So these values, as they are available in the literature, you can use if you want, if the relevant data is not available with you. Okay, so with this we have covered all the dead loads that are associated with a typical uh, tray column. So we considered weight of the shell, we considered weight of the insulation, then weight of the liquid, then we also considered weight of various attachments. Okay, so let us summarize that. So various traces associated due to dead loads, or various stresses induced due to various dead loads. So what are this? Due to weight of the shell, the stress will be induced, and the stress that is induced is FCS, compressive stress. It is given as X into rho S into G. So this is the stress that will be induced due to weight of the shell up to a distance of X from the top of the shell. Then we saw due to weight of the insulation, the stress induced is compressive, and it is given as FCIN is equal to DIN square minus DO square into X into rho in into G divided by 4 into DI plus TS into TS. Okay, then due to weight of the liquid, the stress induced is given by this equation. FCL is equal to X minus LD upon S minus 1 into pi by 4 into DI minus HD square into HW into rho L divided by pi into DI plus TS into TS. So this is again compressive stress. And finally, you have the stress that is induced due to weight of the attachments. So this is given as FCAT is equal to WA upon pi into DI plus TS into TS, where WA represent weight of the attachments associated with the tray column. So total dead load stress then will be addition of all these stresses. That is FDL is equal to FCS, stress due to weight of the shell, FCIN, stress due to weight of the insulation, plus FCL, stress due to weight of the liquid, and plus FAT, that is stress due to weight of the attachment. So in this way, at the end of this discussion, now we know how to analyze, how to get expressions for stresses that will be induced in the wall of the shell due to various dead loads. So with this, I end my discussion. On the stresses induced due to various dead loads associated with a typical tray column. Thanks for watching. Do subscribe to my YouTube channel. Tell your friends to subscribe to my YouTube channel. You please watch my previous videos on uh, tall columns. I'm giving links to those videos in the description section. For time being, have a nice day. Bye bye. See you very soon in my next video.